Okay, this is an extra review lecture. It goes along with Gauss's law and potential. This is the charged cylinder electric field potential example. And upon successful completion of this unit, including the previous units on Gauss's law and potential, including reading your book, attending and paying attention in class, finishing the assigned homework, and reviewing for themselves, the student should be able to correctly answer exam questions and test problems related to the following topics. Apply Gauss's law to a non-conducting long cylinder charge. Determine the electric field inside a non-conducting solid cylinder. Determine the potential difference at points inside the cylinder. Note, please make sure you have reviewed the material on Gauss's law and potential before viewing these slides or videos. You should also review the line of charge example and the sphere charge example in the previous lectures. Determine the potential difference in the long charge rod. Charge of uniform density of 60 nanocoulombs per cubic meter is uniformly distributed throughout a long, non-conducting solid cylindrical rod of radius 6 centimeters. What is the potential difference between point A, which is the inner dashed line here, located 2 centimeters from the axis of the cylinder or the rod, and point B, which is the outer dashed line, located 5 centimeters from the axis of the rod? The first thing you do with any kind of problems is draw a diagram and write down everything you know. And convert all the units to SI, because if you don't convert units to SI in these kind of problems, you wind up with a mess. Okay, knowns and unknowns. The charge density, which we gave the symbol rho, is 6 times 10 to the minus 8 coulombs per cubic meter. And this is, of course, the charge divided by the volume. And this is uniform. The radius of the entire cylinder is 0.0600 meters. The radius at point A is 0.0200 meters. Don't get that confused with the area. The radius of point B is 0.0500 meters. That, of course, is A and B. The physics of this is Gauss's law applied to nonconductors and potential difference. And, of course, this, along with our knowns and unknowns and the diagram and the problem statement, gives us a formula shopping list. Volume for a right cylinder is h pi r squared, where h is the height and r is the radius. And the area for a right cylinder is just the cylinder itself is h times 2 pi r. And of course, this is for height h and radius r. Now you ask me why we don't need the end caps. We don't need them, and I'll explain on the next slide why we don't need them. Also need the Gauss's law, the epsilon naught times the integral v dot dA equals q enclosed. And we can rewrite that as approximation of epsilon naught times the sum of EA cosine theta. And of course, the potential formula is VF minus VI equals minus the integral from the initial to the final point of E dot ds. Take an approach to this. We're going to assume the rod is infinitely long, and we're going to apply Gauss's law to determine the electric field in the rod, and then integrate radially between points A and B to determine the potential difference between those points. Here's our diagram. I added a few more things to it, a little bit more detail. Here's the height of the diagram. Here's the electric field pointing outward. And of course, here's the central axis. Everything is concentric with the central axis. Here, of course, is the inner radius, point A. And of course, point B out here. And of course, we're going to take a Gaussian surface in here. So from experience with a line of charge example, we expect that the electric field is radially outward for a positive charge. We expect that the electric field is perpendicular to the central axis. We expect that the electric field has a cylindrical symmetry, and we're going to choose a Gaussian, concentric Gaussian cylindrical surface of radius little r, and that is the solid line here between these dashed lines. Okay, and the field outside the cylinder must be equivalent, that is for r greater than big R, where big R is the radius of the cylinder itself, must be equivalent to the one we derived for the line of charge. That's this problem. Item 4 in dimensional analysis will be used as a check on the results, and the potential should drop as R increases. Of course, that's for any positive charge as you move further out. We're going to find the net flux phi of the electric field through concentric cylindrical Gaussian surface closed by end caps. And of course, the net flux enclosed integral can be broken into 3 parts as an approximation. Then the flux is going to be the sum of EA cosine theta. And of course, we're going to take the top face, the side, which is the cylinder itself, and the bottom face. Now we recall, of course, angles are normally measured relative to the normal of the surface, not the surface itself. Most people, when they make mistakes on these problems, get the wrong angle because you're using the surface and not the normal to the surface. Now, if you look here, the electric field by cylindrical symmetry and by measurement and experiment all goes radially outward. Okay, any of the vertical components here, any of the ones that run along the axis cancel each other out. So the only things that count, the only place where there's flux going through a surface is the cylinder itself. The end caps, the electric field lies parallel to the surface, and that means, of course, that the cosine, that the normal is 90 degrees to that surface, so the cosine of 90 degrees is 0. So the top and bottom drop out. The only thing you have is the side of the cylinder. And phi then is EA cosine 0. And of course, that's just E times A. And of course, that would be EH times 2 pi r. This, of course, is the area of the cylindrical surface. Gauss's law, Q enclosed equals epsilon naught phi. We just discovered phi on the previous page. So that becomes epsilon naught EH times 2 pi r. And that Q enclosed is just the charge density times the volume of the part of the cylinder that's inside the Gaussian surface, because we're interested in Q enclosed. So this becomes rho times 2 pi h r squared. And of course, r is radius of the Gaussian cylinder, not the cylinder itself. The cylinder itself is big R, so don't get those confused. So it reduces to the electric field equaling rho r divided by 2 epsilon naught. That's inside the cylinder itself. Always check units, because if you don't check units, you can miss things like you have an extra r in here, forgot to cancel out one of the r's. Like I did that the first time I did this problem. I'm like, why don't the units check out? Yeah, that alerted me that I dropped that I made a mistake there. Okay, so E equals rho r divided by 2 epsilon naught. So, of course, we want E to be in newtons per coulomb. Rho is in coulombs per cubic meter. We have an R of meters, and 1 over epsilon naught is Newton meter squared per coulomb squared. When you do all the units canceling, okay, one of the coulombs goes away here, so this one and this one disappears, and the meters cancel out. And we just wind up with newtons per coulomb. For a sphere of uniform charge, E, of course, is rho r divided by 3 epsilon naught inside the sphere. Now, we did the sphere before. Look at, there's very little difference between the two. E is proportional to r for both the sphere and the cylinder. The difference between the two is the way the charges are distributed in the two of this. Here in the sphere, they're all bunched up around one little point. In the cylinder, they're spread out over a long line. So that's the difference. This confirms that we probably did this correctly. Now, we also look at other points too as a background check and just to make sure everything's right. At the surface of the cylinder, R equals big R, and E max, this will be the point where the electric field is a maximum, has to be equal rho times big R divided by 2 epsilon naught. At points outside the cylinder where R is greater than big R, where you're beyond the cylinder, the Q enclosed is just rho 2 pi h big R squared. Okay, so now the Q enclosed, since you're outside the Q enclosed, is all the Q in the cylinder itself, the actual cylinder. Gauss's law says Q enclosed has to equal epsilon naught E out, and we say that E outside, H 2 pi R, where this is, of course, the area of the Gaussian cylinder. So then we can relate that, and it says rho 2 pi h big R squared. To reduce this, E out equals big R squared times rho divided by 2 epsilon naught little r. And of course, rho is just Q divided by h pi r squared. From the definition of charge density, linear charge density is equal to lambda equals Q over h, where h is the long dimension. So we can substitute that, and we find out that rho equals lambda divided by pi big R squared. Substitute it in the previous equation up here for E out, which is right here, where little r is greater than big R, so otherwise you're outside the actual cylinder. Then E out is lambda divided by 2 pi r epsilon naught. And we got this same equation previously in one of the previous lectures. So we now realize that we've probably got this correct. We've checked it multiple ways. And you want to do that before you go on. Otherwise, you make mistakes and you just propagate the mistake. Okay, I forgot to add this into the original recording, so I'm going to put it in here now. Okay, so here's the electric field of a long charged non-conducting cylinder as a plot. Here, of course, is the electric field versus the distance you are from the center. Center is here. Here's at the surface of the cylinder, and of course, going outward. Now, notice here it goes as proportional to R until you reach the surface and E max, and then it falls off as 1 over R. Now, this shape of this curve is exactly the same as it would be for the non-conducting sphere. The only difference would be the height of this, that kind of thing would be the only difference. Now, if this was a conducting cylinder or sphere, E would be 0 until you reach the surface right here. So the curve would be flat along this line here, right? And then it would go to here and drop off as 1 over R. Okay, so we're going back to the original E field that we got inside the cylinder, because that's what we're interested in. So E equals rho R divided by 2 epsilon naught. And the potential difference is VF minus VI equals minus the integral from the initial to the final point of V dot ds. Now, delta V is path independent. It only depends on the endpoints. And E is radially outward at all points. So this means the easiest thing we can do is to integrate over the easiest path. So we're going to go from little r of A to little r of B. So we're going directly between A and B to figure out what the potential difference is between them, because that's what the whole thing is set up for. So we're going to call that delta VAB. That equals negative from A to B of the integral of E dr. Now, the E has a lot of constants in it that we can pull out in front. And of course, the only thing that isn't a constant is the R. And this becomes a very easy integral. So now we have minus the quantity rho divided by 2 epsilon naught times the integral from A to B of R dr. Well, the integral of R dr is just going to be R squared over 2. So we can pull that 2 out too. So now we have minus rho divided by 4 epsilon naught times R squared, and we're going to evaluate that from A to B. Now watch the minus sign here. Because the minus sign, we can flip this around and end up with this. So it will become rho divided by 4 epsilon naught times A squared minus B squared. At this point, we're ready to put the numbers in. Okay, so delta VAB equals our rho, which is 6 times 10 to the minus 8th coulombs per cubic meter. Okay, divided by 4 times epsilon naught, which is 8.85 times 10 to the minus 12th coulombs squared per Newton meter squared, times this quantity here, which is the A squared minus B squared. So A is 0.0200 meters. We're going to square that minus B, which is 0.0500 meters. So we're going to square that. And there's a units conversion, what I call a onesie. 1 volt coulomb per 1 Newton meter. If you go through this carefully and check all the units, you're going to see everything cancels out. The coulombs here, okay, cancel with these. Okay, the meters squared and the meters here all cancel out. The newtons cancel out. The only thing that's left are the volts. Okay, so that means we probably did this correctly, and we didn't do something stupid like drop the square off a meter squared. Yeah, it's very easy to do that. Okay, especially when you typeset something. So delta VAB ends up being negative 3.56 volts. So we expected the change of potential to be a potential drop from A to B, so that's where the negative sign comes from, so we've got that, and the units canceled correctly, so we have a pretty good idea that this worked. For this one, inside a cylinder of charge, we ended with minus 3.56 volts. We did the same thing in a previous lecture for a sphere of charge, a uniform sphere of charge. So delta VAB equals minus rho divided by 6 epsilon naught times R squared from A to B. Put the numbers in there. We wind up with delta VAB equals negative 2.37 volts. There's a slight difference here. It's proportional to R squared, which makes sense. And the reason it's different here is because the charge in the cylinder is spread out over a long line, while that in the sphere is concentrated around a sharp point. It's just the difference in the way the charge is distributed. But both of them have the characteristic R squared dependency of this. So here's some more comparisons. At the surface of the cylinder, E max is rho times big R over 2 epsilon naught. If you plug in the numbers here, with big R being 0.0600 meters, and the rest of it all being the same, you end up with 203 volts per meter. At the surface of the same size sphere, okay, with big R equal 0.0600 meters, you wind up with 136 volts per meter. The reason for, again, is the difference in the way they're spread out. Okay, this one is a long cylinder and this one is a little ball. The potential difference between the center at R equals 0 and the surface at R equals big R for a cylinder, you wind up with minus 6.10 volts, and that's larger than what we got between A and B, because we're going over a bigger distance in the electric field. So yes, you're going to have a bigger potential drop. For the sphere, you wound up with something bigger than we got on the previous page. We went between the center and the surface, and we wound up with negative 4.07 volts. The difference between these is because this is spread out on a long line and this is balled up. Some checkpoint questions. If the long charged cylinder was a conductor instead of a non-conductor, what would the result for the electric field of potential V inside the cylinder? We're going to assume that the cylinder is isolated, in other words, far from other charges. If it's a conductor, what's going to happen is the charges are all going to move to the surface because a conductor, there's no electric field inside a conductor, and it's an equal potential surface. Charges don't like each other, so what do? They go to the surface of a conductor because in a conductor, the charges are free to move. So this means that the electric field inside the cylinder is going to be 0 volts per meter, and the potential inside the cylinder is going to be constant because the whole cylinder becomes an equal potential surface. So be very careful when you have problems like this. Make sure you read all of the questions. And whenever you see something like this down here, they're trying to trick you. So we figured B and D were right. So it's going to be answer E. So be very careful when you do test questions. If the large cylinder was a conductor instead of a non-conductor, what would the results for the E field and potential outside the cylinder be? We're going to again assume the cylinder is isolated far from other charges. Well, once you get outside, only the Q enclosed counts. So it doesn't matter where it is in the cylinder. It can be on the surface. If you're outside the cylinder, Q enclosed is still all the charges on the surface. And since it's the same amount of charge, it's going to be the same. So it won't make any difference. There'll be no change in the answers. They would be the same as those outside of non-conducting cylinders, and that is the same as those outside a long line of charge. So you get the same answers. When you're outside, it's the same, regardless. After I got done doing this, I realized it was a little unrealistic. We assumed that there was nothing else inside the cylinder except the charges. Now, it'll be awful hard to hold those charges in place because they're all positive charges. They're going to want to run screaming out of that cylinder. So you're going to have to put them in some sort of material or charge material. And I assume there'd be like a dielectric material, which would be like a plastic. It's obviously non-conducting. So these equations, the previous equations, were derived assuming the dielectric material of the cylinder has a dielectric constant of kappa equals 1, which is what it would be for a vacuum by definition. If kappa is not equal to 1, then you use epsilon equals kappa epsilon naught. And this means you substitute this any place there was an epsilon naught. And we're going to assume kappa is constant throughout the cylinder. In other words, it's made out of uniform material, which makes sense. Then E equals rho R divided by 2 kappa epsilon naught. And delta VAB, all you have to do is substitute kappa epsilon naught everywhere you had an epsilon naught. So it becomes minus rho divided by 2 kappa epsilon naught times the integral from A to B of R dr. And of course, that becomes minus rho divided by 4 kappa epsilon naught times R squared evaluated from A to B. And of course, if you put in the limits, this becomes rho divided by 4 kappa epsilon naught times the quantity A squared minus B squared. So adding the dielectric material has the usual effect of weakening the electric field and lowering the potential difference. And this would be a more realistic version of this. Thank you.